So everything that we've ever done, we need to undo. Like we did exponential functions, so we had to learn logarithms. We did trig, so we had to learn arctrig. So this is the same thing for what we're looking at in 4.9. We know how to do the derivative of something, so how do we undo that and do the antiderivative of a function? So there are actually two terms up here on the top of the page, antiderivatives and integration. This chapter, chapter 5, is called integration. And so you know that when you are finding the derivative, the process is called differentiation. So you have those two words, one for the process and one for the end result, the derivative and differentiation. That's what these two words are. The antiderivative is the end result, but the process is usually called integration. So these two words are going to be used interchangeably. They're both about finding the antiderivative of something. So integration is more of a process of finding the end result, antiderivative. Okay. It kind of makes more sense in the case of derivative because differentiation and derivatives sort of sound more alike, although they only have the D letter in common pretty much because they are spelled completely differently. But again, these are just those two words, the same things. Integration is the process of finding the antiderivative. So when you see those two words, we use them interchangeably, like integrate something or find the antiderivative of something. You know, one is the do what you need to do, one is get the goal. Okay, so again, there's just notation, some notes on this about just oppositing the things like we mentioned. And there are some notes down here about antiderivatives. And so a function, usually if we have our function little f of x, the notation for its antiderivative would be capital F. So capital F is the antiderivative, and so we could say capital F prime is little f. So if you are given a function f of x, we had a notation for its derivative. We said f prime. The notation for its antiderivative is just the capital letter of the function, so capital F of x. Okay. In order to find the antiderivatives, we have to train our brains to think backwards. So if we're looking at the function f of x equals 2x, we need to figure out what the original function would have looked like. So you need to know what function gives you 2x as its derivative so that you can figure out what the antiderivative is. So you really need to know your derivatives in order to get your antiderivatives. Which function has 2x as its derivative? X squared, right? So capital f of x could be x squared, right? Because capital F of x prime, the derivative of that is 2x, right? So the antiderivative could be x squared. But it also could be a few other things. There are more than one function. There are actually infinitely many functions who have a derivative of 2x. One of them is x squared, but we also could have capital F of x equals maybe x squared plus 3, right? Because you know that when you take the derivative of that 3 part, it's going to be 0. So there could be some kind of constant added onto it, right? So instead of being able to just say x squared, since we don't know what that constant is going to be, we have to go for a general antiderivative. And so in general, the general antiderivative is going to be capital F of x equals x squared plus c, where c is a constant. Because we don't know what constant might have been for the original function, but any constant would be true for that, right? It could have been a 0 added on, like the first function. It could have been a 3 added on, or a 7/2 subtracted from it. It doesn't matter. So we have our general antiderivatives as well as our specific antiderivatives. Sometimes you'll be given an initial condition, and you can use an initial condition to find the actual function that you were talking about in that place. That would be the specific case. But
we don't know if c is positive or negative.
I don't. And so, right, it's just plus an integer, or not even an integer, plus a real number. This real number could be a negative or it could be positive, so we just say plus c, where c is a real number, right? Any real number. So c, the element symbol, again, it's just a real number. It's an element of the real number system. So it could be positive, so you could be adding on a negative there. It doesn't matter, right? C is just some real number that you're adding on. All right, so that brings us to the next page in the back here. That family of antiderivatives, that's what we're talking about for that general function. We're always going to have a family of antiderivatives, so we're always going to have a plus c at the end of our antiderivatives because there's not one answer to these. There's a family of answers. So always add a plus c to the end of your antiderivative. Okay? Okay, so again, there's a bunch of functions here, and we're going to try to figure out what their antiderivatives are based on what we already know about what function gave you that as its derivative. So if you had little g of x equals 11x to the 10th, what function would have given you that 11x to the 10th? Yep, capital G of x is going to be x to the 11th, because if you take its derivative, you would pull the 11 down, subtract 1, and get 10, right? So we're moving that 11 back up into the power, kind of doing the opposite of what we did. We're going to write down some rules for these, or see some rules for these in the next page. But right now we're kind of backwards familiarizing ourselves with what we know the function would have had to be for x to the 10th to be its derivative. Then I'm going to add my plus c, because that was just a family of functions where I have that plus c constant on the end. I don't know, maybe there was something like 2 added on to the end of it or something. So I always want to add that plus c, an arbitrary constant. Okay. What about in the case of little h of x?
Just go to t negative 6.
Okay, so t to the negative 6th plus c. And then if you check that by doing its derivative, negative 6 comes down, subtract 1 from the power, negative 7, so that's working. Yeah, so that's the correct antiderivative family.
And would it matter if we just put 1 over t to the 6? Or
No, it doesn't matter if you put 1 over t to the 6 as well. I'd leave it like that just because it's a little more obvious, because the power rule is the differentiation rule if you have it written that way. Yeah. It's okay if you write 1 over t to the 6th, that's fine also, but leaving it is probably preferable. Okay. Okay, so those two use the same property for their derivative. They're both power rule. Now we're looking at some other rules here. Okay, so if I have p of x equals 3 secant squared of x, I need to know a function whose derivative is secant squared of x, right? There is one. Which function's derivative is secant squared of x? Tangent. Yeah, so I'm going to have capital P of x. That 3 is a constant multiple, so it's going to say 3 times tangent of x, right? Plus c. So again, I have to know my derivatives to be able to do my antiderivatives, right? Okay, 3 tangent of x plus any constant will give you the derivative of 3 secant squared of x. There's a note packet up here. You can grab one. Thanks. Okay. All right, in the next one, part D, r of s equals pi. What function's derivative would be pi? Pi s, because s is the variable here. Yep. So capital R of s would be pi s, right? Because any number times s, its derivative is going to be that number, plus c. Okay. Cool. And then the next couple, 1 over s squared plus 1. What function is going to have a derivative of 1 over s squared plus 1? Almost, no. So if you want to think about natural log for a second, I'm going to make a note up here. If your function f of x equals natural log of x, what's its derivative? Oops, I wrote inverse. I did not mean to write that. Its derivative is 1 over x. So if you wanted to go backwards, you would need 1 over x to have an antiderivative of natural log of x, right? So that's this one, right? So in this one, I can't use the power property like I used up here, because if I add 1 to this, I've got x or y to the negative 1, that doesn't work. Here instead, I need to think that this is the same thing as 1 over y. So the antiderivative of 1 over y must be natural log of y. Yeah. So just as a property, because the derivative of natural log of y is 1 over y, then I have to have the antiderivative of 1 over y being natural log of y. Okay. So that was a good thing to think about for g of s over here. However, natural log just gives you 1 over the input. That's not going to work on this one. There is another function whose derivative gives me that fraction, 1 over s squared plus 1. Arctangent. Yeah, arctangent. So the ones that gave us fractions were natural log, arctangent, arcsine, and arcsecant. But the arcsine and arcsecant had square roots in the denominator as well, right? 1 over the square root of s squared minus 1, or et cetera. 1 over s, absolute value of s times the square root of s. 1 minus s squared, something like that. Okay, so this one is arctangent. Okay, so capital G of s here is the arctan of s plus c. So the derivative of the arctangent of s, and again, having that formula sheet handy, I see you got yours out, which is perfect. Having that formula sheet handy, you're looking at rule number 21, right? Rule number 21, saying that the derivative of arctangent is 1 over input squared plus 1 times derivative of input, and so that is going to be backwards. I have to know that that is a derivative of something to be able to figure this out. So I have to be familiar with those rules or have them to look at, right? Have that derivative page to look at. Okay, I do have another copy of that page I can hand out again if anyone needs it, but I know you had one from earlier. Okay. All right, so the last two here, if I have a function little w of t equals e to the t, what function would have given this as its derivative? E to the t. Okay, so capital W of t is e to the t plus any constant, because the root e to the t is e to the t. And if I have a function that is negative cosine of 4x, what function would have given this as its derivative? Okay, the derivative of sine is positive cosine, right? So it would have had to have been negative sine of 4x, right? But just a second, if you took the derivative of negative sine of 4x, you would have gotten negative sine of 4x times 4, right? So this has to be negative 1/4 sine of 4x, so that when you do its derivative, plus c again, but when you do its derivative, you can still apply your chain rule. Because the derivative of this function now, negative 1/4 sine of 4x, is negative 1/4 cosine of 4x times 4, and so the 4's would cancel, so they're not there in the derivative. Okay. So they, again, leveling up. This is like a level up from the ones above because you have to think about how to counteract that chain rule, right? All right. Now, again, we did all of those derivatives without writing down any rules for how to find the antiderivatives. We're going to write those rules down soon, but it's all about familiarity with the derivatives and what are we going to need to do. What kind of rules are we going to need are some of the things we're thinking about here. What kind of rules are we going to need to be able to talk about antiderivatives? All right.